Hello, everybody. Welcome to Recitation session for fluid mechanics. This is week 7. This week we will have 4 different questions, and they are mostly related about momentum equation. So let's get started with the first one. This is question 6.2. Here it talks about Newton's second law, and it can be stated in this way: the force is equal to rate of change of momentum. Or it says F is equal to the derivative of mv over d. And taking derivative by parts yields this equation. And the question says this doesn't correspond to F is equal to ma, which is the basic and main Newton's second law. And what's the source of discrepancy? So let me first explain these two different terms. So first of all, the force is equal to rate of change of momentum. And when we say momentum, it is actually equal to mv. So this is mass times velocity gives momentum. So here, this first equation is actually applied to system of particles, while F is equal to ma is applied to only one particle. But of course, they are directly coming from Newton's second law, so they are actually not different from each other. I mean, this one and this one is not different each other. They are just derivative of each other. So knowing that, we have another rule, and you can search your textbook. And also it says Newton's second law is applied to, or it is valid only for constant mass. So here this information is important. So let's get started with the question solution. So the main thing in the question we need to find is the discrepancy between this one and this one. And we need to find why they are different. Sorry. So first of all, we have F is equal to ma, and we also have F is equal to rate of change of momentum over time. And if we take derivative by parts, it's going to give and we have dm over dt. So as you can see, at the first sight, they don't correspond to each other. So let's see if we can solve this issue. So here, as I mentioned, this is only valid for only constant mass. And this is the rule of Newton's second law. So since it is constant mass, dm over dt should be equal to 0. And as you see, we also have this term. So this means we have 0 here. And basically, we will get F is equal to m dv over dt. And since this is acceleration, change of rate of change of velocity over time, we are getting ma. So this means that they are actually same, and both of them are actually correct. So mainly there is no discrepancy, but if there's a discrepancy between this equation and this one. The main reason for that, Newton's second law is applied to constant mass. And when we apply this constant mass rule here, we are just discarding this term, and then we are getting MA. Okay, class, let's continue with second question. This is question 6.7. So we have a balloon rocket, and it is held in place by a force F, and F is here. The pressure inside the balloon is 12 inches of water column. So this means this is the pressure exerted by a column of 12 inches of water. And the nozzle diameter is 0.4 centimeter. The air density is 1.2 kilogram per cubic meter. And we define the exit velocity V and the force F. And we are just neglecting friction and assume the reflow is implicit and irrotational. So that we are just simplifying the question actually. So let me first write what we have. We have diameter as 0.4 centimeter. We have density of air as 1.2 kilogram per cubic meter. And the pressure inside the balloon. So we can actually say this is 1 and this exit is 2. Because in the question, it wants us to find the exit velocity and the force. So that we need to create a relationship inside of the balloon and outside of the balloon. So exit of the balloon. So that we have 2. So inside of the balloon, the pressure is 12 inches of water column. And we actually need to convert this to a more familiar or common term, common unit, such as Pascal. And this is actually Newton per square meter. We are doing that because all other terms are in centimeters, kilogram, cubic meter. So we need to find, we need to use the same unit. So if you remember from previous weeks, previous questions, pressure is equal to specific weight times height. And specific weight was gravitational acceleration times density times, again, height. So here we have 9.81 meter per square second times 1.2 kilogram cubic meter times 12 inches. So 1 inch is, I think, 0.25 something. And it is giving 0.305 meters. And eventually this is going to give almost 30,000 pascals of kilogram or meter square second. And this is another form to explain pressure. And you can also get this from your knowledge. So because Newton is kilogram over meter square second. So for example, if we just directly divide it by square meters, you can get this final unit, and it is going to be Newton over square meters or Pascal. Okay, so we found the pressure inside of this balloon as 2,900. Sorry. 2,989 pascals. So we need to find exit velocity because, we need to find exit velocity. So since we know the pressure, velocity, and level between these 2 points, we can directly get exit velocity. So to do that, we can directly use Bernoulli here. Because we have a constant velocity, it doesn't change. So that we have a steady flow, so we can directly apply. And since we are dealing with the difference of these 2 points, Bernoulli is a very practical application. So let me write Bernoulli explicitly. And we are just going to eliminate some terms. So the first one is the elevation. And we can take these same levels. So we have 0 elevation difference. And on the other hand, we have this exit and it is flowing out. So we have 0 pressure assumption. And another one, of course, we will have some velocity here, but it is very small compared to velocity at this exit point, so that we can also neglect this value. So the only remaining equation, only remaining term is the pressure or specific weight is equal to V square over 2G. And from that, Vt square, which is the exit velocity, will be equal to P1 times 2G over specific weight. And we can actually simplify this more. So because specific weight is equal to rho G, so this is actually rho G. So this will be P1 times 2 rho. So finally, V2 square will be equal to square root of 2 pressure over density. So we can write 2 times the Pascal over 1.2 kilogram per cubic meter. And from here, we can get V2 as 70.6 meter per second. So this is the first question in this question. We need to find exit velocity. And the second one will be finding the force, which is applied on this direction. So since we are applying the force from right to left to hold this balloon in the place, we can say that this direction is positive x. So this is completely up to you. You can also apply reverse. So you can say this side will be positive x. But to make it clear, I'm using the same direction of f as the positive x direction. So this will just change signs. It will not change any value, but eventually you will see either ways will work. Okay. So okay, now find the force. And also, as I mentioned in the first question, also in your textbook or from your lectures, the force is equal to rate of change of momentum. And from your textbook equation 6.10, you will find the simplified version of the momentum equation. And it's actually gives, let me write the full equation. Again, we have control surface out minus in. So this is the momentum equation. So if you remember from week 6, we were using continuity equation. It was very similar to this one, but except right now we are multiplying it by velocity for both of these out and in terms. And when we do that, we will get F is equal to, so let's see the sign. I'm sorry, first of all, this should be in. First of all, we don't have inflow, so that this is 0. And what we have is only outflow. So since we said this is the positive x direction and we have outflow in the positive x direction, this is going to be plus. And we have mass flow rate and velocity, and mass flow was rho area and V, and we have additional V, which is coming for momentum. We can get 1.2 kilogram per cubic meter times area, which is PD square root 4. So we have P, we have 4, and we have square of diameter. It was 0.4 centimeters, so it will be 0.004 square meters times velocity. Actually, square of velocity, because now we have two terms. And this is giving the force as 0.0751 Newton. Let's continue with question 6.13. So here we have a horizontal water jet at the 70 Fahrenheit, and it issues from a circular orifice in a large tank. So as we mentioned, we had this horizontal water jet, and this is the circular orifice. The jet strikes a vertical plate, which is here, this vertical plate, that is normal to the axis of the jet. So it is normal to the jet. A force of 600 pound force is needed to hold the plate in place against the action of the jet. So this means that we need to apply a force to hold this plate in this place. So since we have a force which is coming from here, from left to right, because of the water jet, and as you can imagine, it will be very powerful. It can actually move this plate with the force. But to hold the plate in place, we are applying an opposite force which is F, and which is given as 600 pound force. So if the pressure in the tank is 25 psi at point A, what's the diameter of the jet just downstream of the orifice? So we need to find the diameter of the jet downstream of the orifice. So we are actually finding this diameter. So actually, this question will be very similar to the previous one because we have a system and we have an outflow, we have momentum, we have force. So mostly we will follow the same methodology. So let me write a few things. First of all, PA is 25 psig. So pressure is 25 psig here. And we have this outflow. And also, as you can imagine, when we apply this water jet, it will split into these two directions. So this can be mv2, mass flow rate times velocity, and O3. However, in this question, we don't need to deal with these vertical ones because we have horizontal force and we need to find diameter. So we can just use this x direction and use these values. So let's say this is m dot v. So again, from your textbook, you can see that you can apply the same equation. It is because the force is equal to rate of change of momentum, and we will have out minus in. So to find the diameter, we need to do something with force, but before that we need to find actually velocity because it will be used in this momentum equation. So let's find that. So let's say Bernoulli A and B, and let's call this B, this point. So we have PA, comma, so similar to previous question, we have points at the same level. So we just discarded them. And also inside of this large tank, the velocity will be very, very slow. So we can also neglect the velocity inside of the tank. And also we will not have pressure because it is going to atmosphere. So we can just also remove them. And what we have is PA over gamma is equal to VV square over 2G. So this is going to be the exit velocity, which will help us to find the force. So PA is 25 psig and specific weight is, sorry. So we can actually here use this as rho g, and we also have g. So this will cancel each other out. So we will have PA over rho. And from the table, I don't remember it from table 8.6, 8.5. You can find the density of water for this 70 Fahrenheit as 1.94 slab cubic feet. So we have 1.94. And this is actually pound force per square inch. And here, since we are dealing with feet, we just need to convert this to feet. So to make it feet, we can say 1 feet is equal to 12 inch. So we have square here, inch square. So 144 inch square will be equal to 1 feet square. So that we will get pound force over feet square here. And let me to final form. We will have 25 for 44 over 1.94 slab over cubic feet. And from here, we can find velocity. This is equal to PV square over 2. And from here, we can get exit velocity as 60.92 feet per second. Okay, so we now have calculated the velocity at this exit, and we need to find diameter again at the exit of this orifice. And also I forgot to write, we have force on this direction, at this direction. And again, similar to the previous question, we can just assume this, from right to left is positive x direction, so that we can define signs for each term. Okay, now we can focus on the second part of the question, which is we need to find a diameter of the jet. So that we need to use the momentum equation. So because rate of change of momentum is equal to force, so this is actually momentum rate. So we need to change, and also this one, of course. We need to find the change of momentum rate. So as we always do when we talk about change, it is actually out minus, it's actually out minus inflow. So if you look at this plate closely, and we actually don't need to use these vertical forces for now, at least for this question. So here we can say that if you consider this plate, we have an inflow coming through this plate. So we have mi1 vi, mass flow rate times velocity, which is momentum rate. And we don't have any momentum rate as outflow. Because we only have this coming flow as E, because it is considered as inflow. and we have this force, but we don't have any outflow, so it will be 0. And here you can think we have these flows, but since they are vertical at the x direction, we don't have anything for out. So knowing that, we can directly discard this out. And what we have is in. And also another important thing, as I mentioned it at the beginning of the question, we have positive x direction if it is coming from right to left. But here, in this case, we have flow coming from left to right, so that this should be actually minus based on the direction assumption. So we have minus m dot e ve, and this gives positive m and v. And if you do these calculations, the rest is actually easier, because mass flow rate is rho a v, and this is going to give rho a v square. And we already know the value of force, and this will be equal to Fx. So here, since we need to find diameter, we can leave the area alone, which is this value. So we have area is equal to Fx over rho v square. And F is 600 pound force. Rho is 1.94 slug over cubic feet times the velocity we found, 60.92 feet per second square. And from here, the area is 0.0833 square feet. And of course, this is equal to p d square over 4. And from that, we can get diameter as 0.326 feet. Okay, this is the final question, 6.20. And we have a conveyor belt like this one. Discharges gravel into a barge is here, is shown at a rate of 40 cubic yards per minute. So we have, let's say, flow rate, because it is kind of flowing gravel into this barge. And if the gravel weighs 120 pound force per cubic feet, what is the tension in the hawser that secures the barge to the dock? So we are actually asked to find tension. So we will have this tension because this hawser will try to pull this barge to the dock, so that we will see a tension from right to left. Because you can imagine that we have this barge, we have this hawser, and it will pull it here. So based on that, we can actually create a diagram. So we have weight. let's say we have weight, and we will have a corresponding buoyancy force. So they will balance each other, and we will have tension from right to left. So first, let's start with a more common term for the flow rate. So it is 40 cubic yard per minute. This will be equal to 18 cubic feet per second. And also here the question was given, the velocity was given in the question, and the velocity is 15 feet per second. Okay, so since we need to find the tension here, and I actually forgot to add velocity, and the velocity is coming with 20 degree. So we will have this force because of the momentum rate because of the force. So it will be mv but with a 20 degree. So basically we will have tension, and we will have horizontal component of the momentum rate here. So let's see what we get. So again, since we are dealing with force, which is the tension is also force, so we can again use the rate of change of momentum equation. So we will have out and minus in. And here we refer to tension as force. And let's say x is from left to right. So this is positive x. So again, as I mentioned in previous questions, this is just an assumption. So it will just change signs and nothing will matter at the end. So we have minus t because it is coming from right to left. We are dealing with this bunch. So we have in, which is a momentum right coming into this barge, but we don't have any outflow. So that again, we can remove the out part. We only deal with in part. So it can confuse about here. So we can say we have out, we don't have in, but actually here the control volume is barge, so that we are dealing with in or out. And actually let me draw the control surface. And it is control volume. Therefore, we only have inflow. And we have this vertical and horizontal components of this momentum rate. So that and since it is on the from left to right, which is given here, it will be positive. Positive, positive. But since we are doing out minus in, it will have minus sign. So we get minus mv. And since we have angle of 20, it will be mv cosinus 20. And mass flow rate, which is m, is rho a v. And here actually in the question, this value is actually specific weight. So specific weight is equal to 120 pound force per cubic feet. And we need to find rho. So if we use this form, specific weight is equal to rho times g. Rho is actually equal to specific weight over acceleration, gravitational acceleration. So we have minus specific weight over g times a v times v. And here we actually can use q, because q is equal to va, velocity times area, which is coming from continuity equation. And the velocity is 15 feet per second. So the main reason using q instead of a, v, and we don't have anything related to size. So we are directly finding as flow rate, because the flow rate was already given. So we can directly write 18 cubic feet per second. So this is going to be minus, actually let me write it here. We have q, which is 18 cubic feet per second times 15 feet per second. Just wanted to move it. And since this second velocity term has cosine 20, cosine is 20, it will be cosine 20, then this is going to give 945.8 pound force. And it is coming because we have minus t is equal to minus 445.8 pound force. So t will be equal to this value.